Today we're covering chapter 3.1 through 3.2, and we're going to be talking about atomic masses. That's that other number on the periodic table associated with each element. While we're talking about atomic masses, we're going to talk about the mole and molar masses. The mole, by the way, is the chemist's dozen, and the chemist's dozen's number is actually Avogadro's number. We'll do some example calculations, and eventually we'll do some calculations where we determine an actual number of atoms in a sample. Okay, let's get started with a little bit of review. We're asked to convert 13,720 micrometers to centimeters. Well, we have a metric calculation before us. We're using our units, and that starts with step 1. We're after centimeters. Then, step 2, we're looking for a number with a single unit to start the calculation with, and of course that's at 13,720 micrometers. And now time for step 3. Let's get out of that initial unit, so out of micrometers. Getting this far should be pretty easy. Now comes the challenging part, if there is a challenging part. Can we go straight from micrometers to centimeters? And the way that we do metric conversions, the answer is no. To go from one prefix unit into another, we have to go through the base unit. In this case, that's meters. Then from meters, we can go anywhere we wish, including centimeters. For the numbers, remember the base 10 number always goes where? With the base units. So the meters, the grams, the liters, or whatever your base unit is, happens to get the 10. The micros, the nanos, the centis, the kilos always get a 1. And now 1 micrometer, like 1 micro anything, is 10 to the negative 6. Whereas 1 centimeter, like 1 centi anything, is 10 to the negative 2. My original number has 4 significant figures, so I'm going to have 4 in my final answer. My original number is 1.372 times 10 to the 4. Now I'm going to add that 4 to the negative 6 and then subtract the negative 2. 4 plus negative 6 is negative 2. Negative 2 minus negative 2 would be 0. How many covalent bonds does carbon want to form? Well, let's get out our periodic tables, and we'll see that carbon is in group 4A. That means it wants 4 more electrons, so it's going to form 4 bonds. And give the formula of the ionic compound containing the following ions, and we have the aluminum ion and the chloride ion. Well, that plus 3 for the aluminum gives us a bonding number of 3. The negative 1 for the chloride gives it a bonding number of 1. Step 1. Step 2, the easy step, the least common multiple of 3 and 1 is 3, which tells us what? That positive 3 is balancing negative 3. And hence we're going to need 1 aluminum for positive 3 and 3 chlorides for negative 3. When we have aluminum and oxygen, aluminum still has a bonding number of 3. Oxygen we can see has a bonding number of 2. This time the least common multiple is 6, telling us positive 6 is balancing negative 6. So we need 2 aluminums for positive 6 and 3 oxides for negative 6. Next we're after the formula of aluminum nitride, which has the aluminum ion and the nitride ion. Well, each of them have a bonding number of 3. Least common multiple then would be 3. So positive 3 is balancing negative 3. So 1 aluminum and 1 nitride. So do note when you combine aluminum with a negative 1 ion, a negative 2 ion, and a negative 3 ion, what formulas we get for those products. Okay, name the following, and here we have a molecular compound. Remember, if you have nothing but nonmetals, it's molecular. And this is where you use the prefix system, so nitrogen trifluoride. Next, we have 2 chlorines and 1 oxygen, so dichlorine oxide. Another molecular compound, a carbon with 4 chlorines, carbon tetrachloride. And this is one of the many oxides of nitrogen. 2 nitrogens and 5 oxygens for dinitrogen pentoxide. Again, these are all molecular compounds, and we could tell that because they were nothing but nonmetals. When we see a metal, that's our big clue that we have an ionic compound. And now, what is the formula of the cyanide ion? Well, is there a cyano element? I normally means a single element. No, this is one of those 2 oddballs, meaning one of the 2 polyatomic ions that had an "ide" suffix. And I hope you remember the formula, Cn-1. Both of these oddballs have 2 elements with a -1 charge. The other one is hydroxide, OH, -1. Okay, next we're after sulfide. Is there a sulf element? Yes, sulfur. And it has an expected charge of -2. Sulfur wants to gain 2 electrons to be like argon. And now the formula of the nitrite ion. Well, ites and eights have oxygens, and we begin by asking, how many oxygens does nitrate have? Well, nitrogen is in that 7. It's in period 2, so nitrate has 3 oxygens. Ites are always 1 less. Lastly, we need the charge, and that comes from the bonding number of the non-oxygen. The bonding number of nitrogen is 3. Is this one of our 2 exceptions? Yes. Remember, when you have an exception, and those are carbon and nitrogen, you would reduce the bonding number by 2. So that's where we got the -1. So there's 2 things we need for one of these polyatomic ions: the number of oxygens and the charge. The oxygens we got from the position of the nitrogen in the periodic table. The charge we got from the bonding number of the nitrogen. Okay, let's name this compound, and I see a metal, so it's ionic. So it's the name of the cation followed by the name of the anion, and it's always written in that order. So what's the name of our cation? Sr is strontium. Does strontium get a Roman numeral? No, it's a group 2A element, so it's always +2, so just strontium. And now the name of our anion. Well, phosphorus all by itself is phosphide. Again, single elements, ides. We have 3 suffixes, ides, ites, and eights. The guys with the T's, ites and eights, have oxygens. The ides is just a single element, all by itself, with the exception of cyanide and hydroxide. Okay, let's name this compound. 2 chromiums and 3 oxygens. Well, chromiums are metals, so the name of that metal, chromium. Does chromium get a Roman numeral? Yes, it does. We'll figure that out in a moment, so leave an empty spot behind for it. Now the name of the anion, oxide. So chromium, Roman numeral, oxide. Now what's the expected charge on a single oxide? Well, that's -2. Oxygen trying to gain 2 electrons to be like neon. Okay, that's 1 oxide. 3 oxides is -6. And that -6, of course, is balanced by +6. When we divide that by the 2 chromiums, we see that each one is +3. For chromium, Roman numeral 3, oxide. And now for the name of the next guy. Again, I see a metal and a polyatomic ion, so that tells me this is ionic. What's the name of the cation? Cobalt. Does cobalt get a Roman numeral? Yes, it does, and that means we're leaving an empty spot behind for it, just like we did in the previous problem. And now the name of the anion. Well, how many oxygens does phosphate have? Well, phosphorus is not in that 7, so that means that it has 4. Remember, if your non-oxygen is in the 7, it has 3 oxygens for the 8 suffix. If it's not in the 7, it has 4. Okay, phosphate has 4, so here, with 3 oxygens, 1 less, that must be phosphite. Okay, the bonding number of phosphorus is 3, and it's not one of our 2 exceptions, so phosphite has a charge of -3. So that cobalt must have a charge of +3. For cobalt, Roman numeral 3, phosphite. And again, that -3 was for the whole phosphite ion, not just 1 oxygen. So when you have a polyatomic ion, don't look at the oxygens for the charge. Okay, and the name of the next guy, the name of the metal, lead. Does lead get a Roman numeral? Yes. Name of the anion, oxide. Charge on each oxide is -2. 2 -2s is -4. So the charge on the lead is +4. For lead, Roman numeral 4, oxide. Okay, name this compound. Well, I see a metal, so it's ionic. What's the name of that metal? Silver. Does silver get a Roman numeral? No, even though it's in the part of the periodic table where everybody around it has a Roman numeral, it's part of that little triangle, meaning those elements have a constant charge, so it's just silver. And the name of the anion? Sulfide. What's the name of this compound? Well, we have an ionic compound, so what's the name of our cation? Potassium. Does potassium get a Roman numeral? No. The name of the anion? Well, how many oxygens does phosphate have? 4. So this must be phosphite. Again, all we need to know is the number of oxygens for the ate suffix. 1 less is an ite, 2 less is an hypoananite. 1 more would be a perananate. Okay, what's the name of this compound? Well, what's the name of that cation? Lead. Does lead get a Roman numeral? Yes. Name of the anion? Nitride. So lead, Roman numeral, nitride. The expected charge on a single nitride is -3. 4 -3s is -12. And what do we know about that -12? It's balanced by +12. Divide that by the 3 leads, or +4 each. For lead, Roman numeral 4, nitride. Now, what's the name of this compound? Well, we have a cation here and an anion. So the name of that cation? Manganese. Does manganese get a Roman numeral? Yes, it does. Name of the anion? Well, how many oxygens does nitrate have? Nitrogen is in period 2, and so 3 oxygens. So there's nitrate. What's the charge on the nitrate? Well, that comes from the bonding number of the nitrogen. The bonding number of nitrogen is 3. Nitrogen wants to gain 3 electrons to be like neon, so that's its bonding number, 3. It is one of our 2 exceptions, so we reduce that bonding number by 2 for -1. 2 -1s is -2, which of course must be balanced by +2 for manganese, Roman numeral 2, nitrate. And now what is the formula of cobalt-3 sulfite? Well, first we have cobalt-3, meaning cobalt with a +3 charge, and there's its bonding number. Then sulfite. Well, we have oxygens when we have ites and ates, and we will begin by asking how many oxygens does sulfate have? Sulfate has 4, so sulfite has 3. And now the charge on the sulfite, the bonding number of sulfur is 2, and it isn't one of our 2 exceptions, so -2. And that charges its bonding number. So bonding number 3, bonding number 2, least common multiple of 6, says +6, which takes 2 cobalts, is balanced by -6, which takes a single sulfite. This will be 3 sulfites. And now name this compound. I see a metal, so it's ionic. What's the name of that metal? Barium. Does barium get a Roman numeral? No. Name of the anion? Well, this was on our other list, and that was that one that's really hard to predict. Oxalate. Barium oxalate. And now the formula of chromium-3 sulfate. Well, chromium-3, Cr+3. Anything has sulfur, ates and ites have oxygens, and now how many oxygens does sulfate have? 4. And the bonding number of sulfur is 2, and it's not an exception, so -2. Again, our charges are our bonding number, so bonding number 3, bonding number 2, least common multiple of 6 says +6 is balancing -6. We need 2 chromiums for positive 6 and 3 sulfates for negative 6. We're asked to name the next guy, and that's an acid. It's an oxoacid. So we put our thumb over the hydrogen and ask what's the name of that daughter ion. Well, chlorine with 3 oxygens would be chlorate. And 8 ions come from ic acids. So chloric acid. Now why isn't there a hydro in that? Hydro means no oxygens. Actually, hydro means binary, so just hydrogen and that non-oxygen. And now what's the formula of iron 3 dichromate? Iron, Fe, the 3 plus 3. Dichromate was on our list of other polyatomic ions, so we somehow just need to get that into our memory. Okay, bonding number 3, bonding number 2, these common multiple of 6 says positive 6 is balancing negative 6. So 2 irons and 3 dichromates. And now the name of this compound, well, the name of our cation is iron, and it gets a Roman numeral. The name of our anion, that's one of those 2 oddballs, hydroxide. Now each hydroxide is -1, so what's the charge on the iron? Positive 3. Iron, Roman numeral 3, hydroxide. And now what's the formula of potassium nitride? Well, potassium is K+. Nitride is N-3. So there's our bonding numbers. Bonding number 1, bonding number 3. These come multiple of 3. Says positive 3 is balancing negative 3. We're asked to name this last guy. Well, we have a molecular compound this time. Silicon's a nonmetal. So the name of this compound, silicon tetrafluoride. Remember, we use the prefix system when it's a molecular compound. Okay, on to new material, and we're going to start with atomic mass. The atomic mass of an element is the mass of that element equivalent to the atomic mass of an element is the average mass of all the atoms of that element. And we end up measuring them in this unit called atomic mass units. And this is a unit we only use when we're talking about individual atoms. Now the definition of an atomic mass unit is exactly 1/12 of the mass of a carbon-12 atom. Carbon, important for life. Carbon-12, the most abundant isotope of carbon. And if we take 1/12 of that, what we get is pretty much the average mass of a nuclear particle, protons and neutrons. Then there are molar masses. So this is the mass of an entire mole of an element, and there are 2 definitions that I like. The molar mass of an element is the mass in grams equivalent to the atomic mass of that element. And I forgot to remind you that the atomic mass is that other number that's associated with each element on the periodic table. So when you look at the symbol of any element, the atomic number is that whole number, and then the atomic mass is that fractional number. And it's fractional because it's an average. Remember, an average is you divide by the total, and you should expect a fractional number. Okay, so anyway, there's 2 definitions of molar masses that I like. One is that it's it would be the mass in grams equivalent to the atomic mass of that element. So that means we can just grab that number and use and apply the unit of grams, and that's the mass of 1 mole of that element. And it also would say then that that's the mass of that element that would contain the mole number, also known as Avogadro's number, of that element. We'll be talking about the mole in a moment, and it's simply a number. Think of it as the chemist's dozen. Now, to get any molar masses, we're going to use the periodic table, and this is always available to you. And so, for example, the molar mass of helium, we look at that number and it's 4.00, and molar mass is then that number in grams per mole. For sodium, we see that atomic mass, 22.99, and we apply the units of grams per mole. Now again, we use atomic mass units when we're measuring the masses of individual atoms, and molar masses when we're talking about huge collections, and that means we're talking about grams. And ultimately, that's much more practical to be able to talk about grams of the chemical versus atomic mass units. The atomic mass unit's a unit so small that we really can only measure those masses with such things as mass spectrometers. Not a common tool in the chemist's laboratory. Okay, on to the mole, and the mole in its simplest concept is the chemist's dozen. It's a number that we tend to relate chemicals, atoms, electrons, photons, etc. by. So we tend to count things in terms of moles. Now, this is a bit larger than your normal dozen at 6.022 times 10 to the 23rd items. This would be 622,200 billion. That is tremendously a huge number. And remember, if you had a mass in grams equivalent to the atomic weight of an element, this is how many atoms you would have of that element. But just think of this number as just a number, so we can count pretty much anything in terms of moles. And in chemistry, we pretty much count everything in terms of moles. Molecules, atoms, electrons, photons, etc. Now, a mole of anything contains Avogadro's number of that anything, and so that gives us the conversion factors. That's 6.022 times 10 to the 23rd anythings per mole of anythings, or a mole of anythings per the 6.022 times 10 to the 23rd of those anythings. And so if we want to know how many atoms are in a sample, we'll be using Avogadro's number. And we'll talk about this more in just a little bit. I do want to point out that when we're talking about compounds, molecules is the unit that we talk about for covalent compounds, and formula units is the formal term when we're talking about ionic compounds. A little bit more on Avogadro's number. Again, there's that number, 6.022 times 10 to the 23rd, and it is just a number. You have an example homework that says you have a mole of pennies and you divide it amongst 6 billion people on planet Earth, and then we're asked how rich is everybody, and actually we're going to be really, really rich. But the point of the matter is, the mole is just a number. And as a conversion factor we've already seen, we have 6.022 times 10 to the 23rd entities per mole of entities. So here's an example for gold atoms. At Avogadro's number of gold atoms per mole of gold. Now, molar mass calculations are the most common calculations that we conduct in all of chemistry. We do this way more than anything else. So we need to get used to molar masses. And so, right off the periodic table, we see the atomic mass of magnesium is 24.3, and so the molar mass is 24.3 grams per mole. And so this is how we can take a mass and turn it into moles, or take a number of moles and turn it into mass. We'll know which one we're using when we get there, so don't feel like you need to remember this ahead of time. Let's do some examples. How many moles of gold are in 455 grams of pure gold? Well, we're using our units. That's a good thing. Step 1, we're after moles of gold. Step 2, we're looking for a number with a single unit to start the calculation with, and that's the 455 grams of gold. And now time for step 3, out of grams of gold, can we go straight to moles? Yes, we can. Off the periodic table, we get 197.0 grams per each mole. So that 455 grams is 2.31 moles of gold. Next, we're asked for the number of grams of potassium and 7.25 moles of potassium. We're still using our units. Step 1, we're after grams of potassium. Step 2, of course, we're starting with the 7.25 moles of potassium. And now step 3, out of moles of potassium. And again, getting this far should always be pretty straightforward. Now, can we go straight from moles of potassium to grams of potassium? We sure can. And we're going to get the number right off of the periodic table. 39.1 grams per mole. Again, right off the periodic table. So 7.25 moles is 283 grams. Okay, now when it comes to a compound, the molar mass of a compound is simply the sum of the atoms that make up that compound. So if we had sulfur trioxide, we have 1 sulfur and 3 oxygens. So we would have the molar mass of 1 sulfur added to the molar mass of 3 oxygens. Adding that all together gives us the molar mass of sulfur trioxide. And again, putting together the molar mass of compounds is right up there with going back and forth between grams and moles. And I will point out, if you start in the mass of a subject, almost for sure you're going to turn it into moles in your first step. Okay, this determines the molar masses. And first, for water, we have 2 hydrogens, each at 1.01 grams per mole. I'm getting these numbers right off my periodic table. And the oxygen, 16.00 grams per each mole, or 18.02 grams per each mole. For ammonia, NH3, it is ammonia. We have 1 nitrogen at 14.00 grams per mole, and 3 hydrogens, each at 1.01 grams per mole, or 17.03 grams per mole. Simply the sum of the atoms that make up your compound. And sodium chloride, this time I'm going to call that 22.99 grams per mole. And for chlorine, 35.45 grams per mole, which adds to 58.44 grams per mole. And let me give you a moment to come up with the molar mass of sodium nitrate. You have the mass of 1 sodium, 1 nitrogen, and 3 oxygens. This time I'm only going to the tens place, and that gives me 85.0 grams per mole. So when you need 4 significant figures and when you need 3, well, normally 3 is enough, but sometimes you need an answer with 4. The best answer is, if you're going to give a final answer with 3, use 4 throughout your calculation. If you have a final answer with 4, use 5 throughout your calculation. That's the best answer. But if you want a simple answer, just go with 4. You should always be good with 4. Okay, there are times when we are going to be interested in an actual number of atoms in a sample, and this is when we're going to be breaking out Avogadro's number. Now, we actually seldomly deal with an actual number of atoms. We're going to be counting them much more likely in terms of moles. So we refer to moles on a daily basis. The actual number of atoms, quite a bit more rare. Okay, but we can do that. Let's calculate the number of atoms in 3.18 grams of copper. Well, we are still using our units, and that's a good thing. We're after an actual number of copper atoms. Step 2, I think it's obvious, we're going to start with that 3.18 grams of copper. And now, step 3, let's get out of that initial unit, so out of grams of copper. can we go straight from grams of copper to a number of copper atoms? No, we get to a number of copper atoms from moles. So our first move is from grams and into moles. Then from moles, we can go to an actual number using Avogadro's number. Okay, off the periodic table, I get 63.5 grams per each mole of copper. And Avogadro's number, that's 6.022 times 10 to the 23rd copper atoms per each mole. And I come up with 3.02 times 10 to the 22nd copper atoms. Okay, what about the number of atoms in 12.5 grams of helium? Well, we're still using our units, so step 1, we're after helium atoms. Step 2, we're going to start with that given mass, 12.5 grams of helium. And step 3, let's get out of that unit. And now step 4, not step 4 yet, excuse me. Now we ask the big question, can we go from grams of helium to helium atoms? No. How do we get to an actual number of atoms? From moles. So our first move is from grams of helium and into moles of helium. Then from moles of helium, we can go to an actual number of helium atoms. From the periodic table, I get 4.0, I should have used a third significant figure there, 4.00 grams per each mole. And then Avogadro's number of helium atoms per each mole, or 1.88 times 10 to the 24 helium atoms. Okay, let's practice some of the things that we've learned here today. First, what is a mole as used in chemistry? Well, essentially a mole is a number. Think of it as a chemist's dozen. It's actually Avogadro's number. So could you have a mole of apples? Well, you could count apples in terms of moles. I don't think there's enough apple trees on planet Earth to have a whole mole, but you could count them in terms of moles, just like you could count anything that's not a donut in terms of dozens. And now, what's the molar mass of mercury? Well, using our periodic table, we can see that we have 200.59, and what units go along with that? Grams per mole. Now for the molar mass of a compound, I first need that compound formula. Mercury being +1 and sulfide being -2, I need 2 mercuries and 1 sulfide. And now with that formula, I can see the molar mass is going to be the sum of 2 mercuries, so twice 200.6 grams per mole, and 1 sulfide at 32.1 grams per mole, or 433.3 grams per mole. And now, calculate the number of moles of formula units contained in 24.8 grams of mercury 1 sulfide. We're using our units. Step 1, we're after moles of mercury 1 sulfide. Step 2, I'm looking for a number with a single unit to start the calculation with, and as we've seen so commonly, there's only one number with a single unit given. So step 2 drops in our lap. And now the beginning of step 3, let's get out of that starting unit. And now comes the big question, can we go straight from grams of mercury 1 sulfide to moles of mercury 1 sulfide? We most certainly can. There's our most common calculation in all of chemistry. And we already determined the molar mass. If we hadn't, we'd be doing it right now. And that would be 0.0572 moles of mercury 1 sulfide. What is the molar mass of an element? Well, there's 2 definitions I like. One is that will be the mass of an element in grams equivalent to its atomic weight. Then, the molar mass of an element is the mass of an element in grams that contains Avogadro's number of atoms of that element. If you put them together, that tells you a lot about molar mass. And the molar mass of a compound is the sum of the masses of the elements in that compound. And the molar mass of tin, let me get out my periodic table, 10 SN, and I see 118.7 grams per mole. And for carbon dioxide, you got to love molecular names because the formula just falls right out. It doesn't take any work to come up with a formula. Molecular names, it does take a lot more work when it's an ionic name. Okay, I see 1 carbon, so 12.0 grams per mole. 2 oxygens, that's 16.0 grams per mole, or 44.0 grams per each mole. And now what is the molar mass of tin 2-phosphate? Okay, well tin 2 is SN plus 2. And now anything has phosphorus. Eights and ites also have oxygens. And I use the position of phosphorus in the periodic table to tell me how many oxygens does phosphate have. Is phosphorus in that 7, period 2, or group 7A? No, so phosphate has 4. Lastly, I need a charge, and that comes from the bonding number of the phosphorus. The bonding number of phosphorus is 3, and it's not one of my exceptions, so -3. And of course, those charges are our bonding numbers. Least common multiple of 2 and 3 is 6, telling us positive 6 is balancing -6. There's our formula. But we're not done yet. We're just coming up with a formula. Now the molar mass is the sum of all these elements. So we have 3 tins and 2 phosphorus. And how many oxygens? 2 times 4 for 8 oxygens. Adding up all those molar masses, I come up with 546.1 grams per mole of tin 2-phosphate. Okay, next we're asked to calculate the mass of 12.5 moles of carbon dioxide. Okay, well, step 1, we are using our units. We're after the mass, so grams of carbon dioxide. Then step 2, we're looking for a number with a single unit to start the calculation with. Only one given. It's got to be that 12.5 moles of carbon dioxide. Now the beginning of step 3, let's get out of that initial unit, so out of moles of carbon dioxide. And can we now go straight to grams? Yes, there's our most common calculation in all of chemistry, going back and forth between grams and moles. And earlier we determined the molar mass, well we can do it now, 12.0 for the carbon, twice 16.0 for the oxygen, and that's 44.0 grams per each mole, or 550 grams. I'm putting in scientific notation because that's the only way I can make it clear that this has 3 significant figures associated with it. And now, calculate the number of moles of formula units contained in 1 kilogram of tin 2-phosphate. Well, if we hadn't come up with a formula of tin 2-phosphate, we'd be doing that now as a preliminary step before we start step 1. We're after moles of tin 2-phosphate. Then step 2, we're going to start with the 1 kilogram of tin 2-phosphate. And now step 3, let's get out of kilograms. Can we go straight from kilograms to moles? No, we need to first be in the mass unit of grams. Then from grams, we can go to moles. 1 kilogram, 10 to the positive 3rd grams. Again, your base 10 number going with your base unit. And earlier we determined the molar mass of the tin 2-phosphate at 546.1 grams per mole, or 1.83 moles of tin 2-phosphate. Okay, calculate the number of atoms and 0.0010 grams of uranium. We're using our units. So step 1, we're after the number of atoms. So uranium atoms. Step 2, we're going to start with that 0.0010 grams of uranium. And step 3, let's get out of that initial unit. We found it easy getting this far. And now comes the big question. Can we go straight from grams of uranium to a number of uranium atoms? No, we need to first go into moles of uranium. Then from moles of uranium, can we go to a number of uranium atoms? Most certainly can. From the periodic table, we get 238 grams per each mole of uranium. And Avogadro's number, 6.022 times 10 to the 23rd uranium atoms per each mole. And that 0.001 gram, that's a milligram. That's pretty much a piece of dust. It's going to have 2.5 billion uranium atoms, showing you just how small atoms truly are. The smallest piece of dust has billions of atoms in it. Okay, how many atoms are in 2.5 nanograms, 1/1000th of a gram of mercury? We're still using our units. Step 1, we're after mercury atoms. Step 2, we're starting the calculation with at 2.5 nanograms of mercury. And you know how we start step 3. Out of nanograms of mercury, and can we go straight to mercury atoms? No, we're going to get to mercury atoms from moles, and we're going to get to moles from grams. So first into grams of mercury, then from grams of mercury to moles of mercury, and then finally from moles of mercury to a number of mercury atoms. 1 nanogram, 10 to the -9th gram, base 10 number, still going with the base unit. And then from the periodic table, we see 200.6 grams per mole for the molar mass of mercury. And again, 6.022 times 10 to the 23rd mercury atoms per mole, Avogadro's number. And this sample will be so small we wouldn't even see it. And yet it has 7.5 trillion mercury atoms. I hope you can appreciate just how small atoms are. Okay, that completes our lecture for today, and we learned about atomic masses. Remember, the mole is the chemist's dozen. It's just a number. Don't think of it as being something super special. It's just a number. It's a very big number, but it's just a number. And we learned about Avogadro's number, the mole number. We saw molar masses when we talked about atomic masses. Let's not forget that, because that was our most common calculation in all chemistry, going back and forth between grams and moles. And we saw some examples of calculating molar masses. Remember, the molar mass of a compound is simply the sum of the masses of the elements in that compound. And though rare, we can calculate an actual number of atoms, or for that matter, well, I'll say atoms in a sample.